Good afternoon and welcome to Atria's 10th webinar. We are honored to mark this milestone with two people who are significant in the field of math pedagogy. Dr. Shailesh Shirali is the chief editor of At Right Angles and director of Sahyadri School, Pune. He's been closely connected with the Math Olympiad movement in India. But I think the hat that he's most known by is that of an extraordinary math teacher who, through his classes, his books, and now his articles, has drawn a lot of people into the fold of being math lovers, into sharing the beauty and elegance of mathematics. Welcome, Dr. Shirali. And our second person with us is no less a luminary. Dr. Ravi Subramaniam is professor and director of the Homi Bhabha Center for Science Education, Tata Institute of Fundamental Research in Mumbai, India. His main area of work for the last 2 decades has been in professional development, professional development workshops through research, and he works on the improvement of the learning and teaching of school mathematics. Welcome, sir. He's also on the editorial committee of At Right Angles. I'm sure that the topic of proof has drawn many of you to attend this webinar. I will not say much else. This webinar will be in English, though Dr. Subramaniam has very kindly agreed to at intervals, summarize what Dr. Shirali is saying in Hindi. Over to you both.
Thank you. So, shall I begin?
Yes.
Thank you. Shailesh,
Yes,
thank you, Sneha, for the introduction. Just मुझे ये कहना था कि सबको स्वागत, और जो भी हिंदी में बोलना चाहेंगे या कमेंट्स में लिखना चाहेंगे ज़रूर लिखिएगा, और मैं कोशिश करता हूँ उसकी अनुवाद करने की, और डॉक्टर शिराली भी उसकी जवाब देंगे। कुछ क्लैरिफिकेशन है तो भी आप कमेंट में डाल सकते हैं, और हिंदी के अलावा अन्य भाषाओं में भी आप डाल सकते हैं। ಯಾರಿಗಾದ್ರೂ ಕನ್ನಡದಲ್ಲಿ ಕಮೆಂಟ್ ಮಾಡಬೇಕು ಅಂದರೆ ಅದನ್ನು ನೀವು ಮಾಡ್ಬೋದು, ಬರಿಬೋದು, ಬೇಕಾದರೆ ಕಮೆಂಟ್ ಬಾಕ್ಸಲ್ಲಿ ಅಥವಾ ಕೇಳ್ಬೋದು. ಪ್ರಯತ್ನಿಸ್ತೀವಿ ನಾವು ನಿಮಗೆ ಉತ್ತರ ಕನ್ನಡದಲ್ಲಿ ಕೊಡೋದಕ್ಕೋ ಅಥವಾ ಹಿಂದಿಯಲ್ಲೋ ಇಂಗ್ಲೀಷಲ್ಲೋ ಕೊಡೋದಕ್ಕೆ. ಓಕೆ, ದಟ್ಸ್ ಆಲ್ ಐ ವಾಂಟೆಡ್ ಟು ಸೇ. ಪ್ಲೀಸ್ ಗೋ ಅಹೆಡ್, ಡಾಕ್ಟರ್ ಶಿರಾಲಿ.
Thank you, Ravi. Thank you very much. And thank you, Sneha. So, good afternoon to everyone. The topic that we are taking up today is about proof. It's not only about proof without words, though the article that was shared in the circular was mainly about proof without words. And the reason we have taken it up today is that proof is really one of the very problematic aspects of school mathematics. I think many children stumble over it. It begins to acquire a rather fearsome reputation. And perhaps it is because it has a very formal character to it. It has everything to be set in a certain kind of a format. It is introduced quite late in the school curriculum. And I think that all these reasons combine together to make it a rather fearsome topic. I personally feel that if the visual element in proof is emphasized more, the play element in proof is emphasized more, the puzzle element is emphasized more, and it is also introduced in other contexts, not just geometry. It is my feeling that it will be much more acceptable. It will go down much more easily among children than at present. So today I'm going to start by sharing a few proofs without words, and then towards the end of the presentation we'll perhaps take up a few things which are not proofs without words but proofs in general. So let me just open up the presentation. So here it is. I hope you can all see the screen. So here's a very familiar picture just to introduce the theme. I'm sure everyone has seen this picture. It is the pictorial justification for the claim that a plus b whole squared is equal to a squared plus 2ab plus b squared. And just drawing this picture more or less justifies the statement. You don't have to actually multiply a plus b by a plus b. And as you're all, I'm sure, quite familiar, for the factorization of a squared minus b squared, you have a similar picture, which we are not going to show here. And for the expansion of a plus b plus c whole squared, or as many terms as you want, a plus b plus c plus d whole squared, this exactly the same kind of picture as this works for all these. So it's a sort of nice introduction to the theme. And I'd like to just say this, that in this, or maybe this will come out in the next slide. So the basic problems are these. Given a particular relation or an identity, can you, through your play or ingenuity, make up a figure that justifies that identity, that somehow proves it or convinces you why that is true? And the reverse is also there. Given a figure, can you find an identity which you can deduce from that figure? So I think both these parts are crucial to this subject, and they sort of emphasize the visual element in this particular topic. And to me, it seems that the visual element needs to be emphasized far more in the teaching of mathematics than it is at present. So let's look at a few trigonometric identities. So it is often possible to draw a figure that makes it immediately clear why some trigonometric identity is true. So just as I said in the previous slide, the exercise is worth doing both ways. Given an identity, find a figure that proves it. Given a figure, find an identity that follows from it. So I've got three nice examples here. And the interesting thing about them is that they all use exactly the same figure. So here's a figure in which you see an isosceles triangle in which the equal sides have length 1, and the apex angle has size 2x. So by drawing this angle bisector, or which is the same thing as the perpendicular to the base, you can see that the altitude has length cos x, and half of the base has length sin x. That follows from this triangle here, ABD, which means that the total base is 2 sin x, and the altitude is cos x. So the area of the triangle is sin x times cos x. On the other hand, the same triangle, let's not draw this altitude or angle bisector. Let's draw instead this altitude here from B. Then from this triangle here, this right angle triangle, since this side has length 1 and this angle is 2x, you can see that this side, this length is sine of 2x, which means that if you look at it from this side as base, AC as base, which has length 1, of course, the altitude has length sine 2x. So the area of the triangle is half of sine 2x. Therefore, half of sine 2x must be equal to sine x cos x, which means sine 2x equals 2 sine x cos x. So this is a kind of pictorial proof. Of course, you see, I don't want to be too strict about what is a proof without words. We have written certainly some words out here, so it's not as if no words at all are allowed. But we minimize the words and we try to let the figure speak for itself. So this is the basic idea. So let me show you another identity which follows from exactly the same figure. Once again, you have this isosceles triangle whose apex angle is 2x. However, this time I don't call the equal side as 1 unit long. I make this perpendicular length 1 unit long. Now let's examine all the various parts of this. First of all, if this angle is 2x here at the top, then each of the base angles is 90 minus x, which means that this angle here, EBC, is x, 90 minus x, which is x. So since this side is 1, this side here must be tan x, because EC upon 1 must be tan x, so EC is tan x. In the same way, if you look at this triangle here, AE upon EB is cot of this angle, which means this is cot of 2x. And also this, in the same way, you can see that this is cosec of 2x. Now, so, right, you can, because sine of 2x will be 1 upon this. So this is cosec of 2x. So the equal side of the triangle has length cosec of 2x, but it's also equal to cot 2x plus tan x. So you have got this identity out here. Cosec 2x equals cot of 2x plus tan x. So I hope you liked that proof, because here, what is nice about this is that you have used exactly the same figure, and we have got an entirely different identity following from it. And then it goes on. We've got a third identity. Once again, we go back to that figure. And once again, the apex angle of the triangle is called 2x. And I go back to the equal sides having length 1. AB has length 1. So since this is 1 and this is 2x, the length of this perpendicular is sine of 2x. And this length here, AE, is cos of 2x. And the base, if you remember, we had used that fact in the first figure. If I dropped this perpendicular, then half of the base would be sine of x, which means that the full base, BC, is 2 sine x. And now if you look at this triangle here, BEC, the hypotenuse of this right angle triangle is 2 sine x, and this angle here is x. Therefore, since EC upon BC is sine of x, so we find that EC is equal to 2 sine x multiplied by sine x, which means it is 2 sine squared x. So you have cos 2x plus 2 sine squared x equal to 1, which means, of course, that cos 2x equals 1 minus 2 sine squared x. So that's a very neat proof of a double angle formula, cos 2x equal to 1 minus 2 sine squared x. And the same figure also gives a proof of the other angle, the identity for the sine of the double angle. Look at this. So you have sine of 2x here, and this is 2 sine x. So sine of 2x, so relative to this angle x, this is the adjacent side, and that's the hypotenuse. So sine of 2x divided by 2 sine x is equal to cos x, which means sine of 2x is equal to 2 sine x times cos x. So there you have it. So you have three different identities which have followed essentially from a single figure. There's a fourth one which I have, which is not in this presentation, so I'll just break this right now. So let me now come out of this. Ravi, would you like to comment on this?
ये बहुत ही सुंदर था. सिर्फ एक डायग्राम से इतने सारे प्रूफ्स, और मुझे लगता है कि और भी प्रूफ्स प्रमाण ढूंढ भी सकते हैं. तो एक सवाल था कि जो आपने ट्रायंगल बनाया उसमें 2x लिखा है ऊपर की एंगल की मेजर, लेकिन मुझे लगता है कि ये जनरल है. मतलब ये you given any angle you can draw a triangle corresponding to it, जिसकी vertex angle 2x होगा, और the same proofs will apply. Am I correct? I think it.
That's right. Yes.
Right. So it is not specific to any angle, but it's a general proof. Provided 2x is less than 90, would you say that is a condition for these proofs?
Yes, yeah, quite right.
Okay.
I can show you one more which is more well known, but still it is worth showing. Just give me a moment. As I said, it's fairly well known, but still I'll show it. This is a very interesting figure. I hope you can see it. It's a GeoGebra screen. In a single figure, you can derive the addition identities for both the sine and the cosine. So here you have a rectangle and a line AF, which is drawn from the vertex A to this side here. And we draw a right angle here. This is a right angle. I have not shown it here. Angle FEA is a right angle. So this here is a right angle. And you can see, if I call this here, this pink angle X and this angle Y, then this angle also is X. You can make out, because if this is 90, if this is 90 here, if this is X, then this is 90 minus X here, therefore this is X out here. And this angle here on top is x plus y, because this whole angle is x plus y. Now we can start. Let's call this side as 1. That is AF. If AF is 1, then from this right angle triangle, you'll get that this side is cos of y. And then from this right angle triangle, you'll find that this side is cos x times cos y. From 1, you get cos y and then cos x cos y. And at the same time, this is sin x cos y, because cos y is the hypotenuse of this triangle. So this is sin x cos y. At the same time, and from this triangle, if this is 1, this side here becomes sin y. Because this is sin y and this angle is x, this side becomes sin y cos x, because it's the adjacent angle. Again, since this side is 1 and this angle here is x plus y, this opposite side here becomes sine of x plus y, right? From this right angle triangle. So this side of the rectangle is sine of x plus y, and at the same time it is also equal to sine of x cos y plus sine of y cos x. So you have this nice illustration of the sine identity. Sine of x plus y equals sine x cos y plus sine y cos x. And I won't continue this, because by looking at the other side, you can also get a proof for the cos formula. Cos of x plus y, and you'll find it's equal to cos x cos y minus sin x sin y. I won't prove it here. Okay, so I'll stop this now. I hope you enjoyed this. So my basic feeling is that the way these kinds of ideas need to be used is that we need to allow for some imagination and exploration by the child. So it's really like you're given a figure, can you find some relation which follows from that figure? And different children may come out with different answers. From the same figure, you may find multiple relations coming out, and some of them may be of great interest. Okay, so I'll go back now to my other presentation, the second part of it, which concerns what are known as triangular numbers. Yeah, so I'm sure many of you are familiar with the term triangular numbers. So they are the numbers 1, then 1 plus 2, which equals 3, then 1 plus 2 plus 3, which equals 6, 1 plus 2 plus 3 plus 4, which equals 10, and so on. So you get this sequence: 1, 3, 6, 10, 15, 21, 28, 36, 45, 55, and of course it goes on forever. And it turns out that they have the most wonderful properties and the most interesting connections with not only within themselves, they connect in all kinds of ways, but they also connect with the perfect squares. So they become absolutely ideal for exploring visual proofs. So let's look at the most obvious one, which is quite well known. So let me start with something which is quite well known. So we notice that T2 plus T1, T2 if you remember is 3 and T1 is 1. If you add 3 and 1, you get 4. T3 plus T2, if T3 is 6 and T2 is 3. So if you add 6 and 3, you get 9, which is 3 squared. And it turns out that if you add any two consecutive triangular numbers, the answer is always a perfect square. So more generally, you'll find that T of n plus T of n minus 1 always turns out to be equal to n squared. And this is a very nice proof of it. It is proved in the particular case T5 plus T4 is equal to 5 squared. So what is T5? T5 is 1 plus 2 plus 3 plus 4 plus 5. So it is represented in this staircase 1, 2, 3, 4, and 5. So a staircase of height 5, length 5. Similarly, T4 is an inverted staircase of height 4 and length 4. And they very neatly can be fitted together to make a 5 by 5 square. Now, you will find one feature of this particular proof, which is there in all proofs without words, that it fits generally one particular number, but the way it is made out you can make out clearly that it can be used for any number. That is, it generalizes. Though the diagram is very specific to one particular number. So for example, this has been shown in the case of T4, T5. Well, the same idea will work for T5, T6 or T7, T8 or whatever. So you can sort of conclude. So it's like there's a bit of a gap which is left out here, which the mathematical student sort of fills up on his or her own. So this is quite a well-known one. Let's look at, by the way, there's a nice simple algebraic proof of this, which is not proof without words. So T5 plus T4 is just 1 plus 2 plus 3 plus 4 plus 5 added to 4 plus 3 plus 2 plus 1. And I'm going to arrange them like this: 1, 2, 3, 4, 5, 4, 3, 2, 1. And then adding them vertically, you get 1 and 4, 5, 2 and 3, 5, 3 and 2, 5, 4 and 1, 5, and 5 here. So 5, 5, 5, 5, 5, which are 5 5s, which is 5 squared. So if you add T5 and T4, you get 5 squared. And that this proof works in general, because these sums can always be arranged like this. This is, of course, not a proof without words, but I just thought I'd show it to you. Okay, here's a very interesting relationship, which it's not obvious why it is true. If you add 3 times the triangular number to the previous one, the answer always turns out to be another triangular number. So let's look at 3T2 plus T1. It's 3 times 3, which is 9, plus T1, which is 1. So you get 10. And T1 happens to be the 4th triangular number. Let's try it with 3 and 2. 3T3 plus T2 is 3 times 6, which is 18. 18 added to 3 is 21. That's the 6th triangular number. 3T4 plus T3 is 3 times 10, 30. Plus 6, 36, which is the 8th triangular number. 8th triangular number, 8 times 9 divided by 2. So you can see the pattern is clear, and this diagram is a beautiful proof of this. Look at the elegant way in which this diagram has been constructed. You want to show that 3T5 plus T4 is T10. So what this person who has made up this figure has done is, he has drawn 3 T5s as the 3 green staircases, T5, T5, T5. And then there's a space here which nicely is just enough to fill a T4. In fact, this is a square. So it's really T5, T5 and a square. And then the square we have made as a T5 plus T4. So 3 T5 and T4. And if you look at the overall shape, it is just a T10 because the base is 5 plus 5, 10, and the height is 10. So 3T5 plus T4 equals T10. And now you can see, imagine giving this to a child and saying, can you find some generalization of this? Can you further generalize it? Now you can easily see that this picture can be extended. Why do we need to stop at 3 of them? Why can't we further take it in this direction? And I've done so in the next slide. Here it is. Look at the beautiful picture. So I've got the previous one is just here. We have those 3 T5s and a T4. And then arrange 2 more such squares at the bottom and another T5 here. And the 2 squares can be made up as T5, T4 and another T5, T4. So basically you have got 1, 2, 3, 4, 5, 6 copies of T5 and 3 copies of T4, which together make up a T15. The T15 comes from 5 plus 5 plus 5, so you get T15. So 6 T5 plus 3 T4 is T15. And more generally, you'll find that 6 times Tn plus 3 times the previous one, Tn minus 1, will always be equal to T of 3 times n. How do you get 3 times n? Because there are 3 such layers. So 3 times n, so that's it. And there are obviously infinitely many such relations. You can imagine stacking up still more, and you can just go on and on. So it's a bewildering variety in it. Then here's another interesting connection between the triangular numbers. Now, if you remember one previous slide, I showed you that the sum of consecutive triangular numbers is always a square number. Like T5 and T4 adds up to, how much is T5? 5 times 6 is 15, and T4 is 10. 15 and 10 is 25. So they add up to 25. But surprisingly, the sum of the squares of consecutive triangular numbers is also a square. Look at T3 and T2. What is T3? T3 is 6. T2 is 3. So we add up 6 squared and 3 squared. What do we get? Sorry, it's not a square. Sorry, I made a mistake out here. It is the triangular number corresponding to a square. I'm sorry. There's a mistake in this line out here. So 6 squared plus 3 squared is 45. And 45 turns out to be T9. Then look at T4 squared and T3 squared. What do we get? T4 is 10. T3 is 6. So we are adding up 10 squared and 6 squared. So we get 136. And that turns out to be T of 16, because 16 times 17 divided by 2 is 136. Similarly, T5 squared and T4 squared add up. T5 is 15. T4 is 10. 15 squared and 10 squared is 325. And you get, that is T of 25. 25 times 26 divided by 2. So you can easily guess the general relationship. So please excuse this error out here. It should be the triangular number of a square. And you can see the relationship here. Here it is 9, and here you have a 3. This here is T of 16, and here you had T4. Here you have T of 25 and T of 5. So this number here is turning out to be the square of this. Now I'm going to show you an extremely beautiful way of showing this picture pictorially, of showing this relationship pictorially. So have a look at this. So what I've shown you here is T4 squared plus T3 squared is T16 squared. So let's see, what is T4? These blue dots are T4, right? Can you see that? 1, 2, 3. There are 4 rows of it. They add up. There are 10 of them, 10 blue dots, and they are put into a yellow triangle. And there are T4 copies of them. So 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10. You will count 1, 2 in the second row, 3 in the third row, 4 in the fourth row. So there are T4 copies of T4. So the total number of dots in them is T4 squared. Then in the spaces in between, there's just enough space to squeeze in a T3, inverted T3, which I've showed with the red dots and a green triangle, right? So this is T3 because it's got 6 dots, 3 rows in it. And then there are T3 copies of T3. So here is 1, then the next row has 2 copies, and the next row has 3 copies. So the total number of dots in those triangles is T3 squared. The total number of dots in the whole array is T4 squared plus T3 squared. But if you consider the whole thing as a whole, forget the colors. So how many rows does it have? There are 4 rows of 4 each, which means there are 16 rows altogether. So it's basically a T16, right? Oh, sorry. Again, I have got an error written out. It should be T16, sorry, not T16 squared. T4 squared plus T3 squared is T16. And it's so Tn squared plus T of n minus 1 squared is T of n squared. I must have written this in a hurry, so this extra exponent should not be there. So I hope it's clear what I have tried to do out here. So let me take a pause again at this point. So I'll ask again Ravi to comment on this. Just before he takes over, I'd like to just say that triangular numbers offer immense scope for this kind of play, perhaps more than even pure geometry, because triangular numbers deal with numbers. So they are, they are arrays of discrete objects, which are easy to make, very easy to draw. You can just have dots made. Perhaps there may be even columns in which you have a triangular array of that kind. So they're very familiar figures. And drawing a figure corresponding to a particular relation or deducing a relation from a figure should not be such a difficult task. I feel this is a resource which we have not made use of in school mathematics. So let me take a pause here. Ravi, would you like to say something?
Yes, Shailesh, I think there are some comments which precisely reflect आप जो कह रहे थे उसी लगभग उसी शब्दों में किसी ने कहा है कि टेक्स्ट बुक में क्यों नहीं है ऐसे और होना चाहिए वगैरह, तो वो कमेंट है करके हम छोड़ सकते हैं। लेकिन एक इंटरेस्टिंग सवाल यहाँ आया है कि क्या इसको हम मॉडलिंग कह सकते हैं कि आपने एक नंबर्स की एक आइडेंटिटी आपने चुन लिया और उसको इलस्ट्रेट किया कुछ एग्जाम्पल के दौरान और या मॉडल के दौरान, तो क्या कह सकते हैं कि ये मॉडलिंग द्वारा एक प्रूफ हमने पाया। इसके ऊपर आपकी टिप्पणी क्या रहेगी?
Yeah, it is a form of modeling. You're quite right. It is a way when we say, given a relation, find a picture which illustrates it, or the vice versa. Both are examples of modeling. I understand what you're saying.
Yeah, that's I thought a interesting question and an interesting idea. एक सवाल और है जो हिंदी में है, थोड़ा लंबा है तो मैं पढ़ता हूँ। किसी गणित के एक्सपर्ट द्वारा इस तरह के पैटर्न और प्रूफ खोजना और गणित सीखने वाले के लिए इस तरह की सोचने की प्रक्रिया में पढ़ने में क्या कोई अंतर है? अंतर किसके पूछ रहे हैं कि एक्सपर्ट द्वारा खोजना और गणित की स्टूडेंट। मुझे लगता है कि ये सवाल शायद एक एक्सपर्ट और एक स्टूडेंट के बीच में क्या अंतर रहेगा, अगर ये दोनों ऐसे सोच को अप्रोच करेंगे कि क्या, इसके ऊपर कुछ कमेंट्स।
Okay, now I want to show you one or two proofs. As I said in the beginning, this is not meant to be only proofs without words. It's also proofs which have a visual element in them. So I'm going to now show you a couple of things which are of that kind, and then again I will show you something in the proof without words kind of domain. So the next small subtopic is about magic squares of order 3. As you will know, most people will be very familiar with this. A third order magic square is a 3 by 3 array of distinct numbers such that the numbers in each line, that is each row, each column, each diagonal, have the same total. So here's the question. If the numbers used are the digits from 1 to 9, then what number will occupy the center? What will come right in the center of the magic square? So the well-known magic square is this. Most people remember it by, say, 672 or something like that. And then from 672, you can fit out everything. You'll notice that 5 has come in the middle. So the answer could be 5. That is, this is one possibility. But can you find any other magic square in which there's a number which is not 5? And now, in my experience, children sometimes give this kind of reasoning. They say, it must be 5 because this is the middle of the magic square, and 5 is also the central number from 1 to 9. Therefore, 5 must be in this. Now, to me, that is actually incorrect reasoning. And this is also an example how in the whole subject of proof, you're often going to find reasoning which is actually not really reasoning. It is a sort of false reasoning. So this is an example of false reasoning. There's no reason why, just simply because 5 is the central number from 1 to 9, also 5 should be coming here. That doesn't fit. But children themselves can sometimes come out with interesting proofs, and I'm going to show you one way of doing it. So without assuming that this is the magic square, let's see how the children deduced it. So first of all, if you add up the numbers from 1 to 9, you get 45. In fact, it's the 9th triangular number. 9 times 10 upon 2 is 45. Which means that the magic sum of the triangle, of the magic square is 1/3 of 45, which is 15. Right? Each row and each column must add up to 15. So let's call the central number m. So m is one of the numbers from 1 to 9. So what this child did was to consider different possibilities for m and then just eliminate them one by one. So let's consider the possibility that m is 9. Look at this figure out here in the top left. Now, if n is 9, that means we have finished up the 9. Somewhere around it, there must be an 8, right? So supposing, for example, there's an 8 out here. Then 8 and 9 already add up to 17, and there's nothing out here in the remaining part of that line which will get you to the sum of 15. So this is true no matter where this 8 is. So that means this cannot be 9. That proves that it's an impossibility proof for 9. Similarly, if the middle number is 8, somewhere around it must be a 9, and then 9 and 8 is 17, and again you have the same impossibility. If the middle number is 7, again somewhere around it you'll have 9. 9 and 7 is 16, and you can't get 15. Similarly, if you have 6, again you have 9 somewhere around it, and 9 and 6 is 15. You would need a zero around it. So, and 0 is not available. So that means 9, 8, 7, 6 are all ruled out. Now we consider the numbers from 1 to 4. Supposing you put a 1 in the middle. Now somewhere around it there must be a 2. But if you put a 2 here, then opposite it, since 1 and 2 make up 3, you need 12 out here, but 12 is not available. If you have a 2 here, somewhere around it you must have a 1, but again you will need a 12 somewhere else. If you have a 3 in the middle, somewhere around it you have a 1, but 1 and 3 add up to 4, so you need an 11 somewhere. And if you have a 4, somewhere around it you have a 1, so 1 and 4 add up to 5, you have a 10 somewhere. So it cannot be 1, 2, 3, 4, it cannot be 6, 7, 8, 9, and therefore it has to be 5. So it's very easy to construct the magic square from this point, and this shows a very nice element of proof. It shows that sometimes proof has to be by elimination of everything that is impossible. So if you have eliminated everything that is impossible, then whatever is left must be the answer. So this child has, on her own, she found this answer during one maths club session. Okay, so I'm going to, since we are running out of time, I'm going to show you one. Yeah, by the way, there's another, no, let's leave this. I'll leave this also. If necessary, we'll come back to this later on. Let me show you 3 GeoGebra animations at this stage. And sorry, I have to jump between screen sharing. So let me start by showing you a very famous proof of Pythagoras' theorem, which is pure animation. And it is a proof by a person called Henry Perregard. So here's the animation. So given this right angle triangle ABC, so squares are drawn on top of it out here. And you look at the construction that is used. Through the center of one of the squares, I draw a line which is parallel to the hypotenuse, and another line which is perpendicular to the hypotenuse. So since it goes through the center of the square and the 2 lines are perpendicular to each other, I get 4 pieces which are identical. They are congruent pieces. And this square, this yellow one, I don't do anything to it. So what I have to do is I have to make sure that this yellow and these 4 colored pieces can exactly fit into this other square. So that would make this square equal to the sum of these 2 squares. So let's look at this animation here. So I'm going to slowly move one of the pieces from top here, and it will come down and settle down into this corner. Then, okay, so the green square has come on, green pieces come there. Then the blue one comes here and settles into this corner. Then this comes and settles here. Then this comes and settles here. And finally, this comes and settles here. Now, you need to be very careful when you look at this proof. It looks very convincing, right? You have got these 5 pieces and they're beautifully fitted together to form a square. And it's an extremely convincing proof of Pythagoras' theorem. But you need to be sure that you're not being deceived. For example, this edge, let's take the edge of this blue side here. Does it exactly fit with this yellow edge and the edge of the green? Or is it possible that there's a very thin space left which the eye is not able to make out? Or they overlap and again the eye is not able to make out? We must be absolutely sure that that is not the case. So I won't fill out the full argument out here, but for example, when I move this here, does it exactly fit into this corner? Yes, it will, because this corner, it's this angle here, which is the right angle, which is fitting into this. Then to show that this side exactly fits with the edge of the green one, so which one, let's see, you'll notice that this side here has come from this side of the triangle, and this little piece here is this top part of the square. So this bottom here is from, so not a triangle, it's this part of the square, and this top of here has come from the top of the square. And certainly those two are parallel. So this and this are indeed parallel, so they fit together. So you're not being deceived. So you see, you must make sure that you don't make a mistake of that kind. Now, just to show you why this is important, so I'll show you another example where you can be deceived. Again, this is a famous example, the disappearing square, in which you see out here 4 pieces, a blue triangle, a red triangle, a green shape, and a gray shape. And they're fitting together to make this triangle like this. And now I'm going to rearrange these pieces. In fact, it's only 3 pieces which get rearranged. The gray piece doesn't move at all. So just watch what happens. So at the end of this animation, they seem to have again made up this triangle, and mysteriously one gap has come, one square has entered the picture. If I go back here, that square vanishes and it reappears. Now, how do you explain this mystery? The answer is only by looking at every part of this picture and making sure that it really convinces you. And just to show you, I will reveal the secret out here. Look at this point here. Its x coordinate is 13, its y coordinate is 5. So I'll drag this 13, 5 here. This here is x coordinate is 8, y coordinate is 3. So I'll drag this 8, 3 out here. And after moving this, we have a point here whose x coordinate is 5 and y coordinate 2. So yeah. Now, if the picture seems to suggest that this whole line is a straight line, this hypotenuse of the blue triangle and the hypotenuse of the red triangle, and similarly the original figure, the red triangle and the blue triangle. But if it is indeed a straight line, then these fractions must all have the same. That means the 5 divided by 13 should be equal to 3 divided by 8, should be equal to 2 divided by 5, right? That should be the common slope of that line. But you can easily check that 5 upon 13 is not equal to 3 upon 8, and 3 upon 8 is not equal to 2 upon 5. And once you understand that trick, you can actually make up more of these kinds of things on your own. All right, so this is a well-known paradox called the disappearing square. So let me now go back to, I had one more of this kind. Let me see if I should show it or not. Well, maybe not. I think we are running out of time. If necessary, I'll come back to it. So would you like to comment on this, Ravi? Or would there be any questions on this? That means basically the question is, when you want to have proofs in which you rearrange shapes and show that some relation is true. That's the basic question.
Yeah, just a small thing I noticed in the last thing that you showed, where by rearranging the triangles, you get a gap of 1 square. I mean, the slopes were actually ratios of Fibonacci numbers.
Exactly.
Is there something you'd like to
yes, in fact, the Fibonacci numbers are critical in that. There's a whole theory behind it. It has to do with the fact that if you take, say, Fibonacci numbers are what? Let's start in the middle somewhere, 2, 3, 5, 8. So now you'll find 2 upon 3 and you subtract 3 upon 5, you will get a fraction whose numerator is 1, always. 2 upon 3 minus 3 upon 5, what is it equal to? 10 minus 9, so 1 upon something. Always you'll find that the numerator is 1. So that 1 is made use of in this particular thing, and it's not a coincidence that you've got a square of area 1. So actually the resolution of this is that, so the two triangles seem to have a straight hypotenuse. Actually speaking, in one of them they are bent like this, but this is showing it very exaggerated, and the other one they're bent like this. And that parallelogram, which is very, very tiny, has got an area of 1 unit. So in one shape, in this shape, that missing thing has got 1 unit, and otherwise it goes like this. But it's almost like a straight line. So you're not able to see it. So why am I showing this? It means that when you're trying to have a proof without words, sometimes you have to be very sure that things fit as you think they fit. Sometimes they may not be actually fitting like that. You can be deceived by it.
Okay.
Yeah, sorry, go on, please.
Please finish what you were going to say. I'm sure it's...
No, I just wanted to show, make a general comment that the first proof was what is known as a proof by dissection of Pythagoras' theorem. You may be familiar with Bhaskaracharya's proof, that famous proof in which the triangle a plus b whole square and so on. There are actually 3 different kinds of proofs of Pythagoras' theorem. One uses algebraic identities, and those proofs never go back to Greek times because the Greeks never used algebra in that way. So those are much later proofs, Bhaskaracharya's proof. Similarly, the proof which is called Garfield's proof, senator, the president who became US president. Another kind of proof uses congruence. Euclid's proof is congruence. And then there's a third kind of proof in which you cut up and rearrange pieces to get the other thing. That's the proof by dissection. So you have these 3 entirely different kinds of proofs of Pythagoras' theorem. And it's quite amazing that in each category there are so many of them. I just thought I would say that here.
Yeah, thank you. I think that's very useful, and I'm sure people, मुझे लगता है कि लोग इसके ऊपर भी काफ़ी एक्सप्लोर कर सकते हैं पाइथागोरस प्रमेय की अलग-अलग प्रमाण कैसे होते हैं और किस तरीके के. मुझे लगता है कि कुछ 400-500 से ज़्यादा प्रूफ्स शायद है उपलब्ध है और ये ढूंढ सकते हैं. तो एक शायद अभी कुछ सवालें हैं यहाँ पे जो 1-2 मैं पूछूंगा और उसके बाद शायद स्नेहा जी आना चाहेंगे. तो आपने काफ़ी सारे चीज़ों के बारे में प्रमाण आपने दिखाया जो बिना शब्द के हैं, प्रूफ्स विदाउट वर्ड्स. लेकिन ये क्या जहाँ चाहिए हमें ये मिल सकता है क्या? जैसे कि प्राइम नंबर्स के बारे में कुछ प्रमेय है, कुछ थियरम्स है, तो उनके भी कुछ विजुअल प्रूफ्स या प्रूफ्स विदाउट वर्ड्स मिल सकते हैं?
You're asking me. It is possible. It may not. In some cases, these proofs, yes, you can always sort of put it into a visual form, but it may not sort of make it particularly simpler. But I can tell you one which you can try. We may not have time to go into it right now. But if you take any prime number more than 3, that means apart from just 2 and 3, anything from 5 onwards, if you square it, you can show that it will leave a remainder 1 when divided by 24. Now, this can be shown visually. Well, it can be. I mean, I don't think there is time to show it here. But basically, you're looking at how the numbers are arranged in terms of the remainder when you divide by 3, the remainder when you divide by 4, and so on. So you look at various possibilities, and it can. So you're thinking of p squared minus 1, which is basically p minus 1 times p plus 1. So by looking at the number line, you can always show that p minus 1 and p plus 1, between them, they contain enough factors to give you a factor of 24. You can show it nicely visually on the number line. It's sort of a half a visual proof. It's not a fully visual proof.
Lovely.
Fibonacci numbers, relations about Fibonacci numbers, there are lots which can be shown visually. I didn't show them here, but there are so many.
Nice. Yeah, thank you. Right. So, Sneha, do you want to take over?
I have some interesting questions here. A lot of appreciation, Dr. Shirali, and a lot of questions on why our textbooks can't have more proofs like this. Before we get into the pedagogical questions, let me just ask you one math question which was posted. The question of proving 0.9999 recurring as 1 requires making several mathematical assumptions. And based on the way numbers are defined, in such cases, aren't we asking students to accept it by faith? Would you like me to repeat the, here, the question is on this.
No, I understood it. Yeah, I would, it's a tricky matter. Yes, this particular question keeps coming up in so many forums. I think basically, I wouldn't say you have to accept it by faith, but you can have a sort of a question and answer kind of a conversation with the child. For example, one way would be to ask, what is the smallest possible number? Suppose you, and after some time, in fact, this actually happened in a conversation which I had with, again, at the 8th standard level. One girl suddenly came up with this discovery, which was original for her. There can be no smallest number. And she was so startled by that fact that you can keep on making this number smaller and smaller by just putting 0.000 and so on. She was completely startled by that discovery. So in a way, this is a connection with this would be, supposing you took this number 0.99999 and you said, what is the difference between this number and 1? Suppose you did 1 minus this number. What kind of a number do you get? So that number is like a very mysterious, ghostly kind of a number. So you begin to see then that there is no gap at all between this number and 1. I wouldn't say you have to accept it on faith, but at the same time, it does involve some ideas which are slightly abstract. Of course, the purely algebraic procedure is there. It's like any recurring decimal which you can show, but children are often not convinced by that. I think an argument of this kind is more likely to convince them. What number could there be between that and 1? That might.
Thank you, Dr. Shah. Yeah. We have questions from Naveen Kumar and Rohini. Both of them are asking pretty much the same thing: how to get children started in their early stages of math learning to look at math as something that offers a lot of possibilities for visual creativity and intuition. Both of you, either of you could answer this.
Maybe Ravi, why don't you respond? I'll say something after that.
जरूर मैं ऑफ कोर्स मैं ये कहूँगा कि शायद डॉक्टर शिराली की इसमें काफ़ी ज़्यादा अनुभव है क्योंकि वो अलग अलग स्टूडेंट्स के साथ इंटरेक्ट करते हैं, लेकिन मुझे लगता है कि ये शुरुआत से ही जब हम बच्चों के साथ सोचने की जब मौका देते हैं, खास करके गणित की कक्षाओं में, जो भी हम गणित की कक्षा में डिस्कस करते हैं, जो भी हम दिखाते हैं, उसके पीछे कारण क्या हो सकता है? जैसे कि छोटे छोटे गणित के ऑपरेशन से भी जब शुरू करते हैं, एडिशन, सब्ट्रैक्शन, सपोज यू सब्ट्रैक्ट सम नंबर फ्रॉम अनदर नंबर, तो ये कैसे कर सकते हैं? और ये करने की ये तरीका क्यों सही है? जो जवाब मिलता है वो सही कैसे हम पता कर सकते हैं? तो दिस एस्पेक्ट ऑफ रीजनिंग I think can be introduced at every stage, not just for groups, but even for solving simple problems right from an young age. That's my feeling. But जैसे मैंने कहा, शायद डॉक्टर शिराली की काफ़ी अनुभव है एक्चुअल बच्चों के साथ, वो पढ़ाते रहे हैं सालों से, और उसके आधार पर वो ज़रूर कुछ कहना चाहेंगे.
Well, I don't have anything different to say, but maybe you said that. But this question of in which there is some open-ended element in it. For example, you're given a relation, whatever, 9 divided by, or 10 divided by 2 equals 5. Now make up a story which illustrates 10 divided by 2 equals 5. So there is an inventive element in it, in which you construct a story in it. Now, in the same way, you can also ask them to construct a diagram. Now, that is slightly more visual, but I think from a very early age, they have to be exposed to that visual medium. There are so many people who say that when you bring in the visual element into your work, your understanding goes up much, much more. You see things, you understand things in a different way. And I think we perhaps don't make use of this this fact enough in our teaching. There is one famous person, one topologist. I was listening to his lecture the other day, and he gives this challenge to his students. He says, every single thing that I say, I want you to figure out, draw a diagram for it. So he really pushes his students very, very hard. He wants even the smallest thing to be translated into a diagram. So that's a very nice challenge. Of course, that's at the college level. But I think, that spirit can be there at the school level also, to find visual, to bring in the visual element into our teaching much, much more. I think they will benefit in all kinds of ways if we do that.
Thank you, Dr. Shirali. I think that we have also covered this in the pullouts, where Padmapriya Shirali has actually described how to teach word problems using visuals, how to do critical thinking, even introduction of algebra. We've covered that quite extensively with very visual ways to teach algebra. But we have a related question from Neha Verma, which says, what is the role of the teacher in this? What support does the teacher give? Because, explorations by the child should be driven by the child, but how does the teacher facilitate this? Ravi, would you like to answer that?
मुझे लगता है कि ये बहुत महत्वपूर्ण सवाल है और काफ़ी मुश्किल भी है ये चैलेंज टीचर को, क्योंकि टीचर्स की आदत होता है, जैसे मैंने भी टीचर रहा हूँ, तो मेरी आदत ये है कि मैं बच्चों को बता दूँ कि जो भी वो सही, पहले तो उत्तर बताने की हम चाहते हैं कि उत्तर बता दें. दूसरे, जब हम देखते हैं कि बच्चा थोड़ा सा भटक रहा है, कुछ दूसरे दिशा में जा रहा है, तो हम उसे ठीक लाइन पर लाना चाहते हैं. लेकिन मुझे लगता है कि इसको हम रेसिस्ट करना चाहिए, बच्चों को थोड़ा फ्री करना चाहिए एक्सप्लोर करने की. अगर वो गलत भी हो तो वो एक्सप्लोर करने दो, वो खुद शायद उसको महसूस होगा कि ये गलत है या कुछ और तरीका हमें ढूंढना चाहिए. तो मुझे लगता है कि ये काफ़ी चैलेंज है कि टीचर ध्यान रखना चाहिए, सपोर्टिव होना चाहिए, लेकिन बच्चों की एजेंसी को रोकना नहीं चाहिए. तो ये मुझे लगता है कि बहुत इम्पोर्टेंट है. दूसरी बात जो डॉक्टर शिराली ने भी बताया कि एक बच्चे की सोच दूसरे बच्चे के सामने पेश करना और आपस में कुछ बातचीत आना चाहिए, ऐसे एक सिचुएशन बनाना. कम्युनिकेशन, बातचीत, जिसको हम कहते हैं रीवॉइसिंग, बच्चे ने कहा कुछ तर्क, पेश किया उसको हमने रिवॉइस करके दूसरे बच्चों के सामने रखते हैं और दूसरे बच्चे क्या सोचते हैं उसके बारे में, ये ऐसे बातचीत को एनकरेज करना मुझे लगता है कि काफी इम्पोर्टेंट है.
Thank you, Ravi. Shailesh, would you like to add anything to that?
No, I think that was said. He said it. Ravi said it quite completely.
We have some mathematical questions coming in, but before that, I just want to take Mr. Munuswami's question. He says, where do we apply this? I understand that proofs are important in the classroom and proofs are important to the teacher. But in real life, where do we ever use a proof? Why do we teach proofs? So I know this is a very, it's opening up a whole new line of thought, but I thought that we should.
I think proof, first of all, it is part of the development of the brain itself. The pleasure of, there's an aesthetic pleasure which we get, I think, and we have had that element in our culture for a very long time. It's thousands of years old, that desire to show something is true. The Greeks had it, the ancient Indians had it, the ancient Chinese had it, to actually be sure that something is true, so that things are not left with a gap. So to that sense of a demonstration, to be able to demonstrate something in its completeness, I think that it gives a kind of completeness to your effort. I would say there's an aesthetic element involved in this, which a child will naturally appreciate. The child will appreciate the difference between simply making a claim, even if it is true, and being able to argue exactly why that is true, whatever that claim is, even whether it's in mathematics or some other field, to be able to actually give the supporting reasons so that it is now on solid ground. I think it gives a kind of stability, security to our way of looking at the world, so that arbitrariness is not there. We don't just simply claim that something is true.
Thank you. Ravi, would you like to add anything to that?
एक डॉक्टर शिराली ने बहुत अच्छा पॉइंट किया कि एस्थेटिक एक्सपीरियंस जो है वो इम्पोर्टेंट है, इससे हमें प्रसन्न हो जाते हैं, हम खुश हो जाते हैं. और भी मुझे लगता है कि प्रूफ करने की जब आदत बढ़ता है तो हम, प्रूफ इज नथिंग बट रीजनिंग, तर्क करना. और जहाँ हम एवरीडे लाइफ में या कहीं पे मीडिया में और कहीं जगह पे जहाँ तर्क गलत तरीके से प्रयोग किया जाता है उसको हम पकड़ पाएंगे. तो मुझे लगता है कि ये आदत जो प्रूफ की और रीजनिंग की, it's the habit of correct reasoning allows one to identify and point out incorrect reasoning, which is very often applied in everyday life. I think that's an important part. The other thing I would say is that when you attempt to arrive at a proof, you discover many things along the way. अब काफ़ी चीज़ें आपके सामने आएंगे, नए चीज़ें जिसके बारे में आपने शायद सोचा नहीं था. शायद आप जिस प्रमेय को आप सिद्ध करना चाहते हैं वो गलत ही होगा, शायद ऐसे भी हो सकता है. तो आप ये डिस्कवरीज भी काफ़ी इम्पोर्टेंट रहेगी, मुझे लगता है.
Thank you both. I think our questioner is quite satisfied with your responses. We have lots of questions coming in, and I think we can just take 2 or 3 more. Here
just
is one from
Neha.
Yes.
Just occurred to me that हम काफ़ी विजुअलाइजेशन के ऊपर हम काफ़ी एम्फसाइज कर रहे हैं. तो एक सवाल उठ सकता है और उठा भी था कि जो विजुअली डिसेबल्ड है, मतलब जिनको विजुअल इम्पेयरमेंट है, तो उनके लिए क्या ये एक्सेस नहीं रहेगा इस तरीके की बिना शब्द की प्रमाण वगैरह. तो मुझे लगता है कि विजुअलाइजेशन सिर्फ एक टर्म है, लेकिन the actual thing behind it is a kind of materialization. It's a materialization of mathematics. और ये हम tactile भी कर सकते हैं. जैसे Pythagoras actually used not diagrams but pebbles, arrangement of pebbles, etc., which is a tactile version of the same. तो मुझे लगता है कि ये सिर्फ विजुअलाइजेशन जो हम ये शब्द प्रयोग कर रहे हैं, इट इज नॉट रिस्ट्रिक्टेड टू जस्ट द विजुअल मोड। तो ये सिर्फ कहना था, सॉरी।
Thank you so much for that. In fact, one of our viewers, Muhammad Umar, has also said that the examination paper should give scope for responses in such ways. Not just for pen and pencil responses, but give space for visual visual responses, diagrams, pictures, and now you are bringing in this idea of tactile representation. So I think that is definitely a way we should think. We have one question here from Kritika. She asks, when we teach arithmetic operations, how can we provide a glimpse of modern algebra which forms the background?
I think that is not so difficult, because in the arithmetic of odd and even itself, you begin to see the structure of odd plus odd equals even, or that whole arithmetic of odd and even. They're just two kinds of entities and the way they relate amongst each other. Or you look at remainders, you look at all numbers in terms of their remainder when you divide by 3, which can be just 0, 1, or 2. And you find the ways in which they connect with each other. I think there are a variety of ways which are great fun, in fact, because there are even nice, it can be connected with cipher, that is coding. You can have codes based on this modular systems and so on. There's a lot of scope which can be introduced at maybe the middle school level for this. Clock arithmetic is another kind of way in which modular arithmetic can be introduced. There is a lot of scope. You don't have to build it into an axiomatic structure that makes it too heavy, but just a fun topic to play with.
Thank you, Dr. Shirali. We will have to close soon. So I would request that the email ID for posting new questions is shared. And if you have any queries, there are some questions about proper resources, and I would direct you to At Right Angles itself. We have so many articles and for all levels, from K to 12. So I would suggest that you look at our magazine for more ideas and more resources. Ravi or Shailesh, would you like to suggest any other resources?
Yeah, in fact, the last page of my presentation was that, so I'll just show it to you, and then we can close after that. Here, so these are some particular items that I was referring to. You can find these somewhere or the other on the internet. Nuggets of number theory, a visual approach, and so on. And the Wikipedia source is also a nice one. Okay, so that's all.
Thank you both very much. And our apologies to the viewers who have posted questions. Since we're running out of time, we will not be able to answer that, but you could email your questions and comments to us at the email ID which was given. Thank you both very much for joining us. It was a very, very valuable session, and I'm so glad to have had you both on this webinar.
Thank you, Sneha. Thank you, Ravi.
Thank you, Shailesh.
Goodbye all.
Very enjoyable. Thank you.